Hello, and welcome to TutorTube, where the Learning Center's lead tutors help you understand challenging course concepts with easy-to-understand videos. My name is Jeff, lead tutor for electrical engineering. In today's video, we will explore number systems. Let's get started. What is a number system? A number system defines how many different numbers we can represent in a single digit. This is the same as saying how much stuff we can represent with a single number. Most places use base 10, also called the decimal system. This means we can use the numbers 0 through 9 in a single digits place. Binary, also known as base 2, uses only 0 and 1 for a single digits place. Likewise, base 8 uses 0 through 7. Base 16 means we can place 0 through 16 in a single digits place. Because we do not normally have a single symbol to represent 10 through 15, we use A through F. A represents 10, B is 11, and so on all the way to F is 15. Think of number systems as different languages that all use the same alphabet. The same symbols are present, but they have different meanings. Any number, regardless of the number system it is using, can be expressed as a polynomial weighting each power of the base against the number in each digits place. For example, the number 154 can be broken up into 100 plus 50 plus 4. But if we choose to factor a power of 10 out of each term, we get 1 times 10 squared plus 5 times 10 to the first plus 4 times 10 to the 0. Notice how the powers of 10 decrease by 1 as we move from the leftmost digit to the right. If we had a fractional part of the number, how would we represent that in a polynomial? Let's say we have 2067.3, and we need to expand it into a polynomial form. Well, we can apply the same pattern as before, but what about the 0.3? If we follow the same pattern to extend past the decimal point, we'll write this as 2 times 10 cubed, plus 0 times 10 squared, plus 6 times 10 to the first, plus 7 times 10 to the 0, plus 3 times 10 to the minus 1. The same pattern applies to numbers of any base, not just base 10. If we were given 221 in base 8, we could expand it as 221, base 8 equals 2 times 8 squared, plus 2 times 8 to the first, plus 1 times 8 to the 0. Notice how instead of each term including a power of 10, now each term includes a power of 8, because the original number is in base 8. Think about how this pattern relates to why we refer to the digits place as 1 place, tens place, etc. We can use this polynomial expansion to allow us to convert numbers in any base to base 10. Just by evaluating the polynomial, we'll get the equivalent number in base 10. Take 1011 in binary, for instance. By evaluating this expression, it will collapse into 11. This tells us that 1011 in binary is 11 in decimal. This also works for fractional numbers, as long as we remember that negative exponents correspond to reciprocal numbers. Expanding 34.4 in octal, which is base 8, gives us 28.5 in decimal. This applies to hexadecimal as well. Remember that the capital letters A, B, etc. correspond to 10, 11, and so on. Because we're no longer restricted to a single digit place here, we can substitute 16 back into the expression. After simplifying, we find that BF6 in hexadecimal is the same as 3062 in decimal. There's no fancy tricks here. This will work for any base converting to base 10. Converting to a base from decimal is slightly more complicated. To convert to a new base, we repeatedly divide by the desired base and collect the remainders in reverse order. This process is repeated until you get a quotient of 0. To show that this works, let's pretend we're going to convert 153 from base 10 to base 10. This is redundant, but the method still works, and we'll show that it does work. Dividing 153 by 10 gives 15 with a remainder of 3. Dividing 15 by 10 gives 1 with a remainder of 5. Dividing 1 by 10 gives 0 with a remainder of 1. Now that we have a quotient of 0, we collect our remainders in the opposite order we found them. This spells out the number 153, which is what we expected, since we didn't really convert bases. So let's try this, where we want to convert 23 into binary. Dividing by 2 over and over again will give the following equations. Listing out the remainders backwards spells out 10111, which is indeed 23 in binary. Now what if the number we're starting with is a fraction? Well, rather than doing long division with decimals, we isolate the decimal portion. If we needed to convert 23.4 to binary, we'd convert 23 by itself first to get 10111. Now we convert 0.4. Whereas previously we divided multiple times, now we'll multiply by the base we want. There are no remainders to collect, but instead we'll note the whole number portions of each result, that is the number to the left of the decimal. Then take the decimal portion of that number and repeat the process. We'll perform a few iterations of this below. We would continue this process until we got 0.0 as a product. Unfortunately, irrational numbers do exist, and so this process isn't guaranteed to terminate anytime soon. However, a handful of decimal places is plenty, especially if you recognize a pattern. Here we can notice that the last step was the same as the first, which means this method will repeat itself forever. So we can collect the first 4 integers that we noted and write them down in the order we collected them. Putting this together with our integer conversion from before gives us 23.4 is equal to 101.011.011001100 and so on. Let's see another example of this. If we were asked to convert 2,595.6875 to base 16, we'd use the same approach. Convert the integer and fractional parts of the number separately, and then add them back together. Starting with the integer portion, we need to divide repeatedly by 16, because 16 is the base we want to convert to. Going through this process will look like this. Notice how our last remainder was 10. All the remainders must be a single digit, so we'll write 10 as a. Collecting the remainders in reverse order gives us a23. Now we'll leave that for now and focus on the fractional piece. Remember, we want to convert to base 16, so we're going to multiply the fractional part by 16 repeatedly while collecting the numbers to the left of the decimal each time. Doing this will look like this. So the first time we multiplied by 16, we got 11 even. That means we note down the 11, which is b in base 16, and remove it from the number, giving us 0. Because we now have 0, our multiplication will only give 0, so we can go ahead and stop here. We collect the whole numbers in the order we got them, so our fractional part will be just b. Now we just add our two results together, so 2,595.6875 in base 10 is a23.b in base 16. We won't always have the luxury of having base 10 as a starting point or end point. So what do we do in those situations? The methods we've learned still work in other bases, but to use them would require us to learn arithmetic in different bases. The methods we learn take advantage of the fact that all the math we need to do works the same as what we're used to. So to avoid learning a new way to do arithmetic, we can use base 10 as a benchmark for our conversion, converting from our starting number to base 10, and then taking that result and converting it to the desired base. Imagine we were asked to convert 141 in base 11 to base 6. If we knew how to do division in base 11, we could use our division method. But rather than doing that, we're going to convert to base 10 first. Using our polynomial expansion, we find that 141 is 166 in base 10. Now we'll divide 166 by 6 over and over and collect the remainders backwards. So we find that 141 in base 11 is 434 in base 6. Conversion isn't the only thing we can do with number systems. Often we need to do arithmetic in these other bases. However, as we learned just now, we want to avoid arithmetic in new bases. So it's best to convert both operands to base 10, do the math, and then convert back to whatever base you need your answer to be in. This seems like extra work, but it's actually faster and you'll make less mistakes. Let's say we need to find a plus b and a minus b for a equals 54 and b equals 32, both in base 7. Let's first convert both of these to base 10. Now, let's do a plus b and a minus b. Now that we have our results, we need to convert them back into base 7, since that's where we started. Let's convert 62 first using our division method. And now let's convert 16. All right, so our final answer is a plus b is 116, and a minus b is 22 in base 7. Let's do one more example. Same operations, but this time with b9 and 93 in base 16. I encourage you to pause and try this yourself, and then verify with my answers. First, we need to convert to base 10. Now let's do our addition and subtraction in base 10 like this. Now convert the results back into base 16. Thank you for watching TutorTube. I hope you enjoyed this video. Please subscribe to our channel for more exciting videos. Check out the links in the description below for more information about the Learning Center and follow us on social media. See you next time.